आप मोबाइल मोबाइल पे हैं सर?
हाँ, मैं मोबाइल पे हूँ।
जी।
तो मैं कोशिश करता हूँ कि मोबाइल से कम से कम इस पे
जी।
से वीडियो लेके और हाँ, become a real problem.
नमन।
सर वो आप प्रेजेंट करना है सर, कीजिए सर।
सर यू नीड एनी हेल्प?
नहीं, हेल्प तो नहीं, मैं भी कोशिश कर रहा हूँ कि प्रेजेंट कर सकूं स्क्रीन
जी।
से ही।
सर ही इज एबल टू गाइड यू सर।
उनको पता होगा सर, उनको पता होगा सर।
कैसे हो?
माइक्रोसॉफ्ट पावर पॉइंट प्रेजेंटेशन खोले वो, उसमें अपनी स्लाइड्स आ जाएगी, उनकी स्लाइड्स आ जाएगी।
हाँ।
शेयर शेयर स्क्रीन। स्क्रीन आया क्या सर मेरा?
आप बोलिए सर।
हाँ आ रहा है। हाँ स्क्रीन आ रहा है सर आपका।
ओके।
हाँ सर, सर सही है।
प्रेजेंटेशन वाला स्क्रीन आया क्या सर?
आ रहा है सर, आ रहा है, सारे स्लाइड्स दिख रहे हैं।
ओके, सो आई थिंक वी विल स्टार्ट है। मैं कोशिश
हाँ
करता हूँ इसमें देने से।
राइट सर।
Okay, sir. Good evening to everybody. I'm extremely sorry for this entire episode, what has happened from last 30, 38, 35 minutes. So I'll be talking about basically the proliferation of Leo constellation, challenges and opportunities. So for the satellites, Leo satellite, I hope you are able to see the slide.
यस सर, यस सर।
Ground versus space, the very first thing which comes in our mind when we talk about that, I'll try to cover as quickly as possible because a lot of time I have lost it. The two things which is very, very common in space, that is a very low temperature is absolute zero, as well as the pressure which is almost 10 to power minus 12 torr. That is the level of the temperature. And the third biggest challenge is the radiation belt, which is causing lot of trouble in the space technology. That is the basically the high energy particles which is getting trapped in this environment, which is nothing but in the form of torus, and that torus is nothing but it treated as a Van Allen belt, which is going for a low orbit as well as a high orbits. So this is very very important for any satellite maker, whether it's a LEO or GEO or deep space missions, to take care about that. And with all these odd conditions, still people would like to go to the environment. That is because uh, the global view which we get because of the satellites, and the satellite has got multiple reasons for to go there. So here this is the slide which talks about the what are the building blocks of the satellites. So basically it is uh, the satellite bus and the payload. That's very essential. So the am 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 I visible?
Yes, sir.
Okay. So here I think lot of echo is coming. So the building block of the satellite, usually what happens is just a minute. Can you give me two? Uh, Hello. So here, what happens is we get structure,
Structure,
mechanism, thermal,
mechanism, thermal,
electric power,
electric power,
telemetry, telecommands,
telemetry, commands,
attitude control
attitude control
for
for
basically
basic
सर आपका मोबाइल और कंप्यूटर दोनों चालू है क्या?
कंप्यूटर पे
कंप्यूटर पे
लिंकिंग
लिंकिंग
है,
है
अभी
अभी
उसमें
उसमें
कोशिश
कोशिश
कर रहा
कर
हूँ
रहा हूँ
स्विच ऑफ
स्टार्ट
करने
करने
की।
की।
I think there are two devices on screen, sir.
हाँ, that's why I am feeling this. Just a minute.
एक का माइक ऑफ कर दीजिए सर, बाकी ठीक है.
हाँ.
सर आपका माइक ऑफ है सर.
Am I audible now?
Yes, sir. But your slides are not visible.
Oh my God. Is it visible now?
Again, it is not visual, sir. It came just and gone back.
Today network is too bad. Not in a position to connect anything.
What's it?
Uh, is it visible now, sir?
No, sir, no.
It says that visible and then again goes off.
Are you
Today's
trying on mobile, sir?
a mobile only I am doing now. Link is
Mobile
not
में
working at all. That is too poor.
अभी आपका स्क्रीन आने वाला है सर.
Arey, that's not.
सर चला गया सर.
No, what's happening? Anyway, I think screen is not coming, but my voice is coming, right?
Yeah, right, sir. आपकी voice is coming, sir.
Okay, so I think
Hello. हाँ हाँ ऊपर ऊपर लैब में लैब. सर पावर पॉइंट मेरे को भेज दीजिए, मैं यहाँ से शेयर कर देता हूँ सर.
अरे 1 GB है सर. अभी आया क्या?
नहीं आया सर.
Start sharing. Stream broadcast. Start broadcast. अभी आया सर स्क्रीन?
सर वापस जा रहा है सर. आता है फिर वापस चला जाता है.
That's the network issue, sir. I'm extremely
नेटवर्क नहीं
sorry.
सर, शायद साइज ज्यादा बड़ा है उसका मोबाइल के हिसाब से.
So nothing is visible, right?
Yeah, nothing is visible.
Okay. Uh, Anyway, I think I will try to speak, but nothing I can do much right now
Yeah,
because
sir. Sir, I keep narrating. Uh, we have some school teacher also.
okay.
So in hybrid mode also you can talk.
Yeah, that's what here it is showing that it is being shared.
But it's not visible, sir.
Mm. Okay, that doesn't matter. I think more than that, at this phase, I may not be able to do much. So, what happens is basically the satellite technology, the two things are very essential. One is the space, what demands. So, space demands basically uh, very essential that it has to work in a very harsh environment, as I told you, approximately zero temperature in the absolute vacuum around 10 to power minus 12 torr, and to provide the service for a duration of the entire mission life. So the for the long duration of the satellite building, that is also very important that we should be in a position to ensure that the satellite is functioning for a very long time. The another thing which is very essential for any satellite is that the satellite we should be in a position to have the autonomous feature in that satellite. That is, whenever the system demands any temperature to be controlled, any pressure to be controlled, any data to be sent, so that autonomous feature it should be invoked in that. The another point which is very demanding for the satellite to be in operation is specialized expertise and skill sets in multiple discipline, because the satellite has got almost all the engineering and physics which is known to human being that is involved in that. So that is a mechanical, electrical, communication, power systems, propulsion systems, controls, and so on. So it is a multidisciplinary system which is needed for a satellite to be operational. And we should have a real good state of the art fabrication and test capability for us. We need to build the satellite. So this is very essential. And for this, to do that, as the time is coming up, we should have basically the sophisticated tools for design, analysis, and evaluation. So when we say this, then it becomes very important that suppose we are from academia side, so we should be in a position to uh, uh, keep such tools through which we should evolve a design. The design tools can be, for example, typically if I take it for thermal design of any satellites, we should have softwares which we can model, CAD model. After that, a finite element model we can develop it, and we should be in a position to uh, predict the thermal performance or the behavior. So this is very important. So that's why it is required that we should be in a position to uh, uh, have such tools when we are talking about academia also. So along with all this, we must ensure that the highest quality and our reliability is ensured. So this is very very important for our satellite to be go into orbit, and the challenges which is required. That also, whether you are able to see the slide now on your screens.
No, sir, no slide.
Uh, because through my laptop also now it is getting connected. So I'm connected to all of you through my slides. Okay. So actually, when we build the satellite, that time there are two, three things which is very important. That is related to the mission planning and execution. How do we plan a mission and how we are going to execute it? This need should be understood it right at the time we conceived the satellite. We should also assess the what are the technologies which are required for satellite building. That technology also should be known to us, and the risk and uncertainty which is involved in qualifying this, that should be known to us. Mass, volume, what are the limitation and constraints are there, those constraints also should be known to us before we put it, and which rocket we are planning to launch a satellite, we should know that, and what should be our in orbit performance, that should be assessed in between. Now, typically, if we take it, then we have a few application. This I require to speak because we should know that what for we are building the satellite. The satellite is usually built for the communications purpose. Typically, like for example, a speech circuit or trunk routes, TV broadcasting, business communication, mobile satellite services or radio networking, data connection, meteorology, disaster warning systems, and so on. Similarly, the satellite can be for the remote sensing applications also. That remote sensing application, when we say, it's basically like agriculture and crops, forest and bioresources, water resources, geology, ocean and coastal application, environment, rural development or urban management, cartographic application, climate modeling. So many times when I deliver a talk in the academia, university or industry, they usually will be worried about what application we should think of building any satellite. So we can pick up the application for building the satellite. Similarly, for example, weather forecasting. Suppose because recently launched one satellite, if you may be recalling, Microsat 2B, and before that we had launched a satellite which was weather forecasting having the very large payload imager and sounder. So imaging is nothing but taking a picture of the environment, but sounding is nothing but taking a picture in the vertical direction. So this is very essential that we should know what kind of satellite and what kind of spectrum range, wavelength we are trying to monitor it. So bigger satellite, we can have a larger payloads. So that was very important as far as the satellite is concerned. But for a smaller satellite, which our university builds, they for them now recently, whenever a satellite for like Ajadi Sat or Microsat 2B, we launched it. So as seen in this slide, if you are able to see, we are having imaging of the cloud as well as we are having a sounding. Sounding is nothing but a vertical imaging. So using this, now like in this slide, if you are whether you are able to see now the slide or not. Hello, am I audible?
You are audible. You
Okay.
are audible.
Only slide is not visible, is it still?
Yeah, slides are not coming.
Okay. So uh, basically then imaging takes place. So when imaging takes place, then recently like milliwave sounder, that also has been validated very well, and in that validation we have seen that data processing is to be done. So data processing, when it is to be done, if the larger satellite is there in the geo constellation, which academia cannot afford, because the cost will be very high, size will be very big, and the launcher also will be very big. In that scenario, the total cost of the satellite plus launcher, it will be typically around 650 to 700 crores. But academia cannot afford it. So academia and present day, the industries, commercial industries, they mostly look for the smaller satellite. In a smaller satellite, like whatever the alternate approach we got is milliwave or microwave humidity sounder. So using that also we can do the weather prediction by taking imaging of the cloud and the cloud's movement. So now we got a satellite which is in the low Earth orbit, typically around 450 kilometers to 500 kilometers. And we got a satellite which is in the geo constellation, approximately 36,000 kilometer. So that is also there, and 36,000 kilometer, the orbit period of the satellite will be approximately 24 hours. So it will be like a geo satellite. So if we take as imaging from the LEO satellites, low Earth orbit satellite, you can get a higher resolution. Higher resolution means even the smaller satellite can give a good picture. And you can, if you can establish, that is the biggest challenge as on today industry is facing about the uh, satellites inter-satellite linking. This is another bigger challenge which is coming through, is from satellite to satellite linking. And if this problem is solved by academians, commercially now it is solved. So what happens is, at a higher frequency we have to go for the data transmission. So like a K band or a KU band or KA band. In that scenario, data transmission takes place, and from low Earth orbit we can communicate to GSO. From there we can download the data from anywhere. So in this way, if by chance any where we want to build the satellite, low Earth orbit satellite for space and disaster management. Typically, for example, if I say that suppose somewhere earthquake has come, some flood has come, drought is there. So the ground structure will be spoiled, but the space networking will be available. So using the satellite images and geo constellation, we will be in a position to communicate to anywhere by through satellite phone, and we can provide the mitigation problems. Now, along with this, another feature which comes for the small satellite is basically the space science, or we can say the quest for the knowledge. So that is nothing but X-ray, astronomy, gamma ray burst, ionosphere, plasma, or middle atmosphere dynamics, how it is changing, because for our Earth environment, that is very essential. So along with that, for example, our equatorial, at equatorial jets are available. So those jets study provides lot of information about our Earth surrounding. So using that also we will be in a position to do lot of physics for the Earth atmosphere. So basically, if I say the low Earth orbit satellite can be adopted for astronomy, astrophysics, and planetary atmosphere. In fact, Netherlands is a front runner in the small satellite known as 10 centimeter cuboid. That's called as a 1U satellite. So 1U, 2U, and forget about low orbit constellation. The Marco 1 and Marco A and Marco B. These two smaller satellite of the 12U size have gone for the Mars orbiter also. So in case we build the satellite, the very important thing is we should know which orbit we are placing. So I have talked about the low Earth orbit. Usually academia or our academic institute, they launch it is typically around 350 to 450 kilometer altitude, and its orbit period will be typically around 90 minutes. And from there, neo orbit or geo orbit, which is at a higher altitude, and for the purpose which we are launching. So once this part is done, then we come into picture that in case we have to build the satellite for the medium class, we should have a launcher also. European countries, as I mentioned to you, like CubeSat, which is from the Netherlands, and it is becoming very popular among the academicians throughout the globe. Uh, there is a rocket called Ismail, which is built by 14 European communities. Similarly, ISRO has built very recently, you might have seen the news of SSLV. We had a PSLV earlier, we had a GSLV, and now a small satellite launch vehicle is already made it up to 150 kg satellite we can launch very easily. So kind of launcher also development is very, very essential. So let me come take an case study of a CubeSat, and I will just talk about the lesson which we have learned from this across the globe. The lesson is something like this. If I have to talk in terms of the science, I can talk that uh, actually around 2018, roughly 250 satellites, small satellites were launched, which were weighing around 1 to 50 kg of that class. And slowly this number grown up to, by 23, it has grown up to approximately 750 numbers. But if this number grows up like this, our future prediction is approximately by 2030 we will be having almost 1 million small satellites around our earth. That's typically around $1.6 billion market for a smaller satellite. And that's the reason why academia throughout our country also should concentrate on is building the small satellite. So for a small satellite of the class of 1 kg to 25, 30 kg or 1 kg to 50 kg, and the size of typically approximately 10 centimeter by 10 centimeter by 10 centimeter, or this is 1U, this can be 10U, 5U, any of that size. So 6U to 12U platforms are very common. So these are called CubeSat. So these CubeSats university are building across the globe. Now, this satellite can be only one satellite, or many universities can come together and build many satellites together. And if they are beginning, this is called as a flight formation. So if many CubeSats are being built, so using inter-satellite link, we can establish the communication. So the another aspect is there for our communication engineers, that we must be in a position to evolve one side. So this is another challenge. I talked about opportunities are plenty for academia. Find it out an application. Based on that application, typically you frame the satellite, what kind of satellites you want to configure, identify the launcher, and in case you are planning for many satellites by many university or one satellite by any single university, then you should be in a position to take the data from the satellite to the ground and utilize it. So this is the second challenge, and usually which is very common and very challenging, very useful, that is synthetic aperture radar. So very precise formation flight can be established. Many universities can join hand, and really they can play a very meaningful output from the satellite to satellite communication, so that we can provide many solutions for the country, for the state, for the specific zone. And usually this is very essential for very large geographical area like our country or Russia. So this is about the flying formation. Similarly, the transformation of on its way to the artificial intelligence. So this kind of automatic diagnostics based on telemetry. Suppose our satellites are there. So these satellites, the telemetry or the commands or the communication which is coming to the ground, that information is available on board satellite also. So based on that information, satellite should have the artificial intelligence to identify, to detect the problem, and also to solve the problem. So the coming days of the satellite technology is important for all small satellite, medium class, and larger satellite is artificially intelligence, which should be automatically built by our signal intelligence. So that also should be an important feature we should train our data. So for automatic learning system for the management of satellite constellation. So this is another challenge which is coming for the academia. So mechanical engineers, electrical engineers for power and solar panel based and battery backup, and communication engineers can build up the communication transmission as well as receiving, and if they can establish the inter-satellite link, so like that. And physics people can come forward for the mathematics and physics for the flight dynamics and mission simulation. So these are the few challenges which I was talking about. But the moment you talk about the communication, the important aspect comes about the data transmission. Usually higher is the frequency, higher will be the data content within the signal. So for example, up to C band and S band, usually smaller satellite, people used to have UHF and VHF band, but for the satellite communication, usually up to 2 gigahertz C band, 2 to 4 gigahertz up to S band, or at a higher frequency, like as on today across the globe people are talking about is Ku band and Ka band, that is 10 to 12 gigahertz or 12 to 18 gigahertz. Higher transmission poses another problem, that we need a higher power dissipation. That heat flux within the satellite will be very high. The moment heat flux becomes high, we should know how to cool the satellite, or how to keep the satellite temperature within the control. Otherwise, that also will pose a problem. So here comes another challenge for academicians or institutes about the optical communication or the laser communication. So this is also becoming very important, because laser communication is in low Earth orbit. It's very common for a satellite which is moving approximately 7 to 8 kilometer per second. So then it becomes very essential that people of communication background should be in a position to solve this problem also, or take part very actively in the communication. Another problem for the smaller satellite is if every university across the globe start launching smaller satellite, then if there is a no regulation is formed, then there will be n number of satellites. As I just now mentioned, almost millions of satellites are going to be there around our earth, creating a debris, space debris, which is going to be a very challenging issue across the globe. And this is what the world is facing now today, because regulations are not there. And in fact, many people, they are sending like Starlink series. They are having 4,500 to 6,000 satellites across the earth, around the earth. Just in that, hardly few will be active, another few will be inactive. Suppose one is failing, immediately another inactive satellite will be made operational. So that's how it is flooded with a small satellite, creating space debris problem. So very important thing comes here is we should have a solution either to deorbit the satellite, which has become now space junk. So you are not able to see my slides, but all these I have shown here pictorially. So we should have a deorbiting capability. So how to have a deorbiting capability? Either we should have a built-in very small propulsion system, thruster kind of scenario, which should push the satellite away from the given orbit. So it should not hit another satellite and damage that active also. So for that we are having a, we call as a drag augmentation devices, or we can call it a magnetic torquer or reaction wheels, that is inertia wheels. So small wheels we can prepare it, and we can keep it at one corner of the cuboid, satellite cuboid, and operate it when the need comes to deorbit the satellite, so that we can avoid it. Now, another challenge which we are facing is that antenna, solar panel which is responsible for power generation, because larger transmission, larger housekeeping, larger payload demands power also high. So larger power means solar panel size will be high. Similarly, if the communication wants to establish high, antenna size will be high for transmission purpose. Now, such a large antenna, we will be our solar panel, we will not be able to accommodate in the smaller satellite. So a Japanese technique called origami. So such kind of technologies universities are following. Very common origami. You may be familiar with which using usually papers. People make various shapes and sizes. So like that, many such kind of folding objects will be made, and that will be transferred or deployed once the satellite reaches into orbit. So origami is nothing but a new high-tech solutions for appendages like antenna and solar panel. So typically, like NASA's RainQ project, this was a very popular project from the origami structure. So it's like an umbrella. It was a folded umbrella when it was launched, but when it reached into orbit, it got deployed like a solar panel also. So I was just mentioning that a smaller satellite not only limited for the communication, Earth observation, but also now the time has come. People have become academicians, have become very knowledgeable. So they are also planning deep space exploration using a smaller satellite. Typically, like NASA has launched two smaller satellite, Marco A and Marco B, for the Mars mission. So it is gathering lot of information. Typically, it was the 6U to 12U class of satellite. I have just now mentioned 1U means 1 unit means typically 10 cubic centimeter, 10 centimeter by 10 centimeter by 10 centimeter, and we built housekeeping as well as the payload within that satellite. So these scientific projects, basically it can be put it there in the smaller satellite, and we can think about putting for the deepest excavation, deep exploration, and new any new technology which university students want to depict or showcase it, that also can be put on a smaller satellite and launched it, so that immediately we get a result and we can do that. So when so many applications are there, so many universities are there, so many commercial industries are there to build a smaller satellite, our low Earth orbit is now flooded with space debris or junk in the orbit. So it is the need of the hour that we should have a new regulations which should not only think about the frequencies, orbit manipulation, quality standard, and deorbiting technologies. But the most important, which I would like to talk about, is the cyber security. Cyber security, people are talking about that in case you don't control your satellite, either wherever you are building the satellite software on ground, that can be attacked. So when the satellite is in orbit, that can destroy the link communication, or control can be taken over by the some other agencies which are hacking your satellites, or they can have a laser weapon and destroy your asset in the orbit. So cyber security is a very big challenge for coming days for a smaller satellite. So how does the future look like? In coming days, we would like to see more and more such a small low Earth orbit or LEO constellation. We see because satellites will be in low Earth orbit, so it can see the resolution of the satellite will be higher compared to higher altitude satellite, and we can take frequent pictures also. Similarly, uh, new architecture will can come up for the satellite because many universities will be working together, and because of this reason, our electronics instrument, electronics engineers, they can build new and smarter components. So that also will solve and have a very big electronic industry, very big fabrication industry in coming days in our country as well as across the globe. So many startup can be thought of it about this kind of application. So manufacturing and production. In fact, if many satellite, some commercialization is there, then if we can have, in fact, like high volume and smaller satellite, it can be in production line can be there. So using that, market can grow. So such satellites were like a slingshot satellite, and like I mentioned about CubeSat, which is 1U, 2U, they are all scalable, and they are like a modular approach. NASA is coming up. There are some challenges in CubeSat or a small satellite. They are coming up the satellite which is like a disk, flying saucer. So the multiple disc will be occupied in the rocket top, and they can be launched with the in the orbit. And once it is launched into orbit, this is going to demonstrate as a standardized launch interface, low launch cost, and simple mechanical and electronics design in 2024. That is the challenging thing which is coming up for the satellite, for basically higher data rates, spectrum contention, and security purpose. So for that, as I mentioned to you, we have a challenge of optical communication, and for that purpose, size, weight, and power aspect, what we call as a SWAP, that is size, weight, and power advantage, such kind of optical communication is very essential to be developed by our engineers, which are working for the space science. So this is the future of academia, government, and industry. So from all three prospects, a small satellite building is the very important aspect for coming days, for solving the common or the societal problem and attending all the disaster which is all around across the globe. And for that purpose, in fact, people are coming with the hybrid architecture also. So I feel that if this problem is solved, then we will be in a position to build the satellite, a smaller satellite, and that will become the future for our country, our university, our academia, as well as the commercial application. So once we slightly safeguard our satellite from the cyber security, we need not worry about that. So very essential is right now there is no straightforward guideline available for building a cyber resilient spacecraft. But yes, in due course, if this also is attended, then I'm pretty sure that this satellite building will become yeah, everybody's job. But in coming days, Pico and nano satellite on chip, they are the future of our satellite. So this is what I wanted to communicate. So there were so many slides, approximately 50 to 60 slides. Unfortunately, due to very poor network at my place, I am not in a position to show you all the slides. But sometimes when I come in person in with all of you, I'll be in a position to showcase myself in a slightly bigger way. Thank you so much.
आलोक सर 9 तक है ये.
Acha. So one thing is there that it's good that time is extended.
Yeah.
So
Actually, time was 7 to 7:50 and 8 to 8 to 8:50. Then 9 to 9:30 was interaction.
acha, acha. Oh, so I thought my time is only up to 8 o'clock.
No, 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 no.
Okay. So
It
let
is
me.
till 9:30. You can carry on.
No, no problem. So the few more things I would like to talk about, because time is permitted for me. So one thing is, as I mentioned to you, the coming days are very, very challenging for a smaller satellite is about the size 1 kg to 25 kg, or up to 50 kg smaller satellite. But when the scope grows, suppose for example, we want to build the telescope, we want to build the messaging service, we want to build the telecommunication service with the 5G 6G media. So basically high and stable platforms when we want to build it, then this low altitude satellites becomes the only solution which is available at a cheaper rate. So they becomes a cheaper solution, they becomes a smarter solution, and they becomes a manageable solution, because if they are a smaller satellite, you can have a multiple satellite building in a short duration, as well as at a much cheaper cost. So at a time, in case suppose one or two or three or four or such number of satellites, you have a problem, immediately so many satellites, they can be in the assembly line, and you can launch them also using a smaller launch vehicle, which is nothing but launcher on demand. So using that, you can replace the satellite which is in orbit, which have gone bad. This solution is not possible for the satellite which is there at a higher altitude, which is bigger in size. So that is a important thing. Here, just one more application of the smaller satellite can be, like for example, we call it is a in orbit servicing. That is, in case we want to correct something or fill the propellant, so we can carry the propellant from here directly and send this smaller satellite to a larger altitude, shift the propellant from our smaller satellite to a larger satellite, and detach the smaller satellite and destroy it. So this becomes like a in orbit servicing. This is another dimension where people are working for the smaller satellite application. So that is in orbit servicing. So here, when we want to do such kind of satellites also, the components which is very essential, where our academicians, students, and industry startup, they should concentrate is about the components like wheels, which is nothing but inertia, inertial wheels we call it typically. So it they basically they work on the gyroscopic principle, and it's like if it is body is rotating about one axis, the satellite can be oriented automatically about the other two directions. So we keep the such inertial wheels around 3 to 4 or 5 corners of the satellite, and we can have demand the rotation in whichever axis we want to rotate it. Similarly, transmitter. So upcoming transmitter also is, I mentioned to you, C band, S band, KU band, or X band. That also can be really looked at it. Similarly, once we go into the orbit, who will communicate to us what is the attitude of the orbit? So attitude determination, star sensor or star camera, this is another very focusing and very challenging technologies, and people have gone for earth sensor based system for attitude control, to star sensor, and those star sensor which were used in a bigger satellite, which were nothing but 5 to 10 stars constellation, they used to look it and talk about the attitude. Now in a smaller satellite, they are micro star sensors which are very much functional and available. So a team which is interested on developing such technologies, smarter technologies, lighter technologies for tomorrow, that can also be concentrated on. Similarly, gyroscope as well as GPS, such kind of instrumentation also is the field in which our academicians can work on it. So technology variations are so many, but the only thing is that they needs to be verified. They needs to be demonstrated, because a system which is working at ground level, they will not be working in space, because as I have mentioned to you in the very first introduction part, that in deep space we have a very low temperature, very low pressure, and radiation build, that is a highly energized particle around Earth. So very important aspect is whether we have got a demanded protection for low temperature, for low pressure, as well as against the radiation shielding. So that's why most of the components, electronic component which we utilize in the satellite, they are known as radiation hardened components. So these radiation hardened components, they are very costly components. Everybody will not be able to afford, typically the university or the startup. So they use a commercially off the shelf, that is called COTS component. So these components are cheaper, but they are vulnerable for failure if some odd situation comes. Like suppose we are not in a position to control the temperature of the satellite, it is having very wide variation. Then it happens that the satellite will not be, the components may fail or they may be vulnerable for fail. So that's why we should be very careful when we are adopting such electronic component. That's why I told that our responsibility of our electronic engineers will be develop such a smart radiation hardened components where they can be utilized for the satellite, and they becomes more and more important because we need miniaturized version, smaller components for providing same service as the bigger components. So these smaller components pose another problem, that as we miniaturize these electronic component, heat flux will be higher. The moment heat flux becomes higher, then another problem comes of is basically thermal control of such components. So these thermal controls, various passive techniques are solution, but not always. So always we should look for the active solution also. So active thermal control is another thermal control where fluid will be involved, power will be involved for controlling the temperature. So like passive radiative coolers are there, thermoelectric coolers are there, or even sometimes the satellite will be in tumbling mode or it will go in the eclipse, that's behind the earth and the sun energy is not available, so it will be cooling drastically. That time we should be having a battery backup and support the power. Battery backup is also very important. So these coming days we started our satellites with a nickel cadmium battery, but it was having its own problem that we the charging, discharging and life was limited. Then came nickel hydrogen battery. Nickel hydrogen battery was supposed to be maintained at a very narrow and low temperature range. Then came lithium ion, which is now the trend in globally, not only in our satellites, but in the mobile, in the automobile, everywhere. Lithium ion battery is very famous. So this lithium ion efficient battery is the power backup source for our cooling satellites. So this is another thing which is coming up, and the satellites are becoming smarter and smarter. What do you mean by that? Basically, the real estate which is available will be smaller and much smaller in the smaller satellite. So what do? We used to embed such power systems within the satellite surfaces itself. We used to have a printed circuit board on the surface itself. No need to have another additional printed circuit board, mount the component, and then make it functional. So many people are coming with a printed circuit board on the surface itself. So so that they becomes a cheaper solution, they becomes a smaller solution, real estate will be controllable. So using that such kind of components, pico and nano satellites are becoming very common in coming days, but of course they are posing lot of challenges in terms of the structure, challenges in terms of the thermal control, and as I told you, antenna and solar panel type of deployable trusses, the origami solution. Many people are coming with the new approaches for storing it or folding them and then deploying in the orbit. So that is another challenge which our the satellite builders are facing that problem. And coming days are like I mentioned to you in 2024, NASA is coming with a solution like a disk sat, like a flying saucer. So there what happens is it is basically satellite on chip. Entire satellite, all the controls, housekeeping controls, along with the payload, it will be built on the chip and that will be launched. That will be well within 1 kg. So just imagine uh, at least a satellite up to 10 ton class of the satellite, which is already flown in the space by various agency. Typically, ISRO has built approximately 6-ton class of satellite. From there to smarter satellite of 1 kg class, having the same approaches. Now, after listening to so many satellites and their variation, the challenges and their opportunities for the space application, the another thing comes which is you may be thinking that why I need to have only one satellite. For example, if I want to build a larger telescope in the orbit, then I can have multiple satellite to build the same purpose. So what happens is there comes the concept of a satellite constellation. That's why we call it as a small satellite constellation or a piecewise building the satellite in space. So one satellite will have one part, another satellite has second part, third satellite will have fourth part. Like that, many satellite we will be building and launching together, and all the satellites will work in a very synchronized manner to address the same objective, and that's what we call as the satellite constellation. The satellite constellation can be in the LEO or it can be in the GEO. The constellation, once you define that is a group of satellites, they work in very coordinated manner. This coordinated manner working is very essential for the large geographical area type of country like our India or USSR or USA. Such larger countries, the flying constellation is very common and becoming very popular also in terms of the smaller satellite. So typically, as many of you might have read the print media news that we are having a Starlink constellation. It is approximately 10 to 25 kgs per satellite, approximately 4,500 to 6,000 smaller satellite, and it will provide Internet of the Things (IoT) throughout the globe, anywhere to anywhere, with a very cheaper rate. So such kind of flying constellation, and by the time, because at a lower altitude the satellite will be moving very fast, but by the time one satellite goes away from the field of view, another satellite occupies. So that way, switching over communication from one satellite to another satellite, that is a very challenging task. So exactly the concept is very similar. Like our mobile, we are traveling from one area to another area. So our mobile emits the signal from our mobile. It will be captured by the tower, and when we are moving across the towers, immediately communication will be sent that this user has gone from this point to this point. Exactly same way, the flight constellation also goes, and we say that this satellite is gone, next satellite has come up, and it will solve the same objective. And typically, this repeat cycles will continue, and within 1.5 hours to two orbits, it will complete the objective. But in case it's a low Earth orbit, we have a pretty many challenges because the satellites are cheaper, components will be vulnerable for failure, but because they are smaller, so assembly line will be there. We can quickly build the satellite. Turnaround time will be very less, so we can quickly build and replace the satellite. And forget about replacing immediately. There will be lot many satellite which will be dormant and they will be available in the orbit. Suppose one satellite goes bad, immediately we can switch over to the another satellite. So Earth observation and communication in both the fields, this flying constellation has become very popular for transmitting and receiving the information from the satellite to the ground. And for this purpose, if it is necessary to reduce these time periods to minute or even seconds, it is essential to have more smaller satellite that also they should work in a coordinated manner. So, how is this number of satellite in a constellation? We should define it. How do we say that we require how many satellites in the orbit? So for this purpose, we have to have a long calculations. In fact, nowadays so many softwares are available, which by through which we can calculate. But we will be in a position to
Sir, any issue? Alok sir? Hello? Sir, any issue, sir? Okay, sure, sure. अभी लाइन ब्रेक हो गई है तो सर इज स्टिल ट्राइंग टू रिजॉइन विद इन शॉर्ट टाइम ही विल डू इट. Just after a few minutes, link for attendance will be given on chat area. So all the participants are requested to fill that positively.
Hello, am I audible?
Sir, you are audible, sir. You are audible.
Hello, am I audible now?
Right, sir, you are audible.
Okay, I have tried to join using the laptop.
Very, very good, sir. Great, sir.
But,
Thank you.
let us just proceed in that way. But slide sharing, I'm not able to do. Doesn't matter. So I will just switch off the video camera and so that bandwidth I'll be able to manage. Extremely sorry today. I don't know what is happening to our location here. Uh, totally signal is down. So I was talking about the flying constellation, which is becoming very challenging day by day, but very useful. So the question comes is how is the number of satellite in a constellation is defined? So during the initial mission design phase, this is the time to decide how many satellites the constellation will have, which is basically the first step is to know the requirement of the project, what for the satellite is being made. So once that is known, then with some basic equations and basic knowledge, which geographical area will the constellation will serve, how often will the satellite receive and transmit information, and also the service for a single country or with a multiple country it will be there, and latency of hours in data access. For example, when we are serving the countries are downloading the data from one point to another point, there will be some delay in the information. For example, satellite is above India, but I want to access the information from some other ground station. So satellite to ground station to ground station, there will be some latency or time delay. So that can be from seconds, minutes to sometimes even in hours also. So that depends upon how many satellites we are having in orbit. So that will be dictated by the number of satellites which we can design it. So the mission design basically it includes an orbit analysis to select the most suitable, and how many satellites is required that will be needed, that can be helped in. To support this process, specific software tools are available for carrying out simulations and for subsequent decision making. So in case our university or for that there may be some free source will be available. Using those freewares also, mathematically our students also can design that kind of software information. So in this design phase, it's also possible to take into account the possibility that the satellite of a constellation transmit information between themselves or directly in space without intermediate points. Suppose we don't have multiple ground station or this thing, then directly it can be downloaded. So in this way, many information from satellite to satellite, as I mentioned to you, or satellite to ground station and ground station to ground station. So this kind of high speed link can be established and constellation can be defined. So what are the biggest challenges if I talk about in a smaller satellite? It will be data processing, whether it should be done after receiving all the data at the ground, or a smarter satellite where we can process the data in the onboard or in the satellite itself and transmit only useful product down at the ground level. So these are the two different challenges which satellite makers are finding. One is data processing at a ground level or data processing in the onboard satellites when autonomy is built. So communication. Suppose satellite is above India and we don't have any ground station we are on the Indian land mass or even sea surfaces. Then what happens is all the information which satellite has captured, we need to store it. So communicate and store, both all these three things, data processing, communication and storage, they are the major challenge which as on today people are trying to address it. So lots of satellites create a lot of data. Lot of data means data processing more data in orbit, so the constellation can downlink only what is needed. Otherwise, the lot of garbage will be available at the ground which is not useful. So if you can process on board, that also will be very essential, that you can only download which is useful information. The second challenge will be building a smaller satellite constellation responsively. They can also serve military, humanitarian and civil purposes related to, for example, crisis situation. For this to happen, the space industry has to get familiarization with industrialization. So many of the industries also they should come forward in building the satellite, realizing them, then testing it, after testing it, transporting it appropriately without damaging it from the satellite building area to the launch pad. So these two, three challenges are after building the satellite. Now, let me just talk for another 5 to 10 minutes about the last slide. What are the disadvantage? We cannot say that always we have advantage of a smaller satellite. Always which we have the there is no use of bigger satellite and so on. Please remember, I never meant that. I never meant that all coming days only smaller satellite will be there, because please remember that orbit slots are the costliest asset any country has. For example, we have a 5 to 6 slots. These 5 to 6 slots in the same slot, typically, like, let me talk about like 74-degree east, 82.5-degree east. These are our 55-degree, 101.5. These are our typical slots for India. Now, if I keep a satellite there, then I have lost my. Then you mean to say that India can have only 5 6 satellite? As and today, for your information, we are having close to 52 satellites if they are orbiting in our Indian sky. So how many satellites we can put it in one slot? Many. How do we do that? We do co-location. So in the same slot with some or angular dispersion and narrower bandwidth, we can keep multiple satellite with a co-location and utilize in a better way. So I am not saying that bigger satellites are useless, but and only smaller satellites are important. A smaller satellite, nano satellite, there are all disadvantages also. What is that disadvantage? Despite their innovations, nano satellites still poses some limitations compared to the bigger and even smaller satellite. So nano satellites, though smaller in size, easily we can build it, faster we can build it, faster we can launch it. But compared to smaller satellite, will continue to be used for different application. It is hard to fit solar panels, so power generation is a limitation. So because large area is not available, so we cannot generate more power. When we cannot generate more power, a powerful communication cannot be established. Powerful radar cannot be there, because framework will be smaller, structure will be smaller. So extra electrical power is not available. In fact, people are also looking for nuclear solutions for this, but that is right now it's a dream only. Right now that is not becoming a solution, because in case due to any accident, if we lose the satellite, it will be a threat to residents on Earth. So this is one bigger disadvantage for the nano satellite. Another is a limitation. Another limitation for the nano satellite is the attitude control. And this I have talked about earlier, that in case we are not able to control the satellites attitude, they will be having a problem of collisions with each other, and there will be unfavorable mass to surface area ratio for both spacecraft and smaller reaction. So reaction wheels, if they are not built in, thrusters if we have not built in, then lots of space debris will be there around Earth. That also I have talked about it. That is another disadvantage of the nano satellites. So we should come out with a rules regulation for industry, for academia, for building the smaller satellite. And as I mentioned to you, that's the last point I would like to communicate to you, that very popular among the universities, American universities, European universities, Australian universities, and you can also do the survey of that, is CubeSats. So I have already talked about it. Based on that only, I was talking for so long about the smaller satellite. So this main CubeSat disadvantage is a small mass and size. It means that suppose I want to build the a larger telescope for deep space exploration, I cannot do that. I have to increase the satellite size, but CubeSat cannot have it. A powerful transmitter, a transponder, I want to build it, but I cannot build it because the size of the satellite is very small. So payload size also becomes smaller only. So they are having a limitation that what kind of satellite this smaller satellite can serve the purpose. So there are advantages, but there are disadvantages also. So unless and until appropriate propulsion systems, transmission systems, frequency coordination, and such kind of appropriate smart structure with the proper thermal control is not there, a powerful smarter satellite cannot be built. So that's what I wanted to talk about today in this talk. Thank you so much. So I'm available for any kind of communication which our audience today, whoever are there, if they want to have it. I hope I'm able to explain myself.
Sir, the slides which you have just applied in your
Yeah,
presentation,
yeah.
can you email to me afterwards?
Yeah, I will share it to you so that you will be in a position to share with all the audience, and they
Fine.
can go through once again,
Yeah.
and they themselves are almost many of the things I have talked about. They will be in a position to easily understand it. I'll share with your email ID.
Okay, right, sir. Thank you, sir. Thank you. Any question from the participant side? Unfortunately, we got stuck in this situation.
Yeah,
So, so no one is responsible for that. It is just a network issue.
yeah. In fact,
And
not able to see that at the fag end only I got the network, but
right,
still the bandwidth is not adequate to share the
yeah,
presentation. Otherwise, in another 15 minutes, I would have glanced through the
yeah,
slide. But anyway, I'll be sharing the slide presentation, which
right, sir.
people can go through it.
Yeah, sir. I remember when last time, I think in 2017-18, uh, when we had conducted a 2-day workshop on
Yeah,
Academic Institute Nano Satellites. So we had invited Dr. Alok sir, and he is very talented and very renowned personality in ISRO. Most of the time, whenever the launch is there in Sriharikota, Dr. Alok is used to be there. If you watch him on the screen, and he used to do some sort of commentary, I think, sir.
yeah, that is true. So live coverage. I
Right.
used to do that. Even people, for example, they would like to listen. They can just Google and see that how Mars was inserted into orbit. What happened the Chandrayaan 2 when we were about to land on the moon's surface. All this is available with a great explanation during the for 30 minutes to 1 hour launch. You can Google by my name. it will come and you can watch it very interesting commentaries there about detail.
Right. Any question from participant side?
Sir, I have, hello.
Yeah, Chauhan. Yeah.
Sir, I have a question like out of topic. What you have said, I just wanted to know like what computer science engineer or computer engineers do at ISRO.
Okay, that's very good question. As I think I was mentioning it very clearly, you name the engineering and the engineers are involved here. Computer engineers are involved. I think one talk might have been given by Rajiv Chetwani there, who is our alumni in our college. Basically, for the embedded softwares, the software evaluation, the control softwares, all this is done by our computer engineers, and also they take a very frequent active participation in the flight dynamics, flight calculations, and those software development, as well as the software development for the data acquisition at the ground station, and make it a display telemetry telecommand. All this is done by computer engineers.
No longer.
And sir, any kind of research is also being done from company engineers.
I couldn't get you. Can you come up? Come on again.
So, any kind of research has been like ongoing or it's been done in the past by computer engineer, like kind of deep space mission kind of research and things.
Yeah, I just now mentioned, and I'll tell you, last week I was there in NASA. I have seen plenty of computer engineers doing the flight dynamics calculations and building the softwares for navigation, for controls, and lot of research is going on. And it's actually, as I mentioned to you, the cyber threat for our digital asset is really going to be a big challenge. Which our computer engineers are only solving it. So there are lot of support is there from computer engineers, because a lot of digital assets are there from various countries into deep space.
Okay, thank you, sir. And can you give me some small tips? Like, I'm a computer engineer pursuing MTech, and I really had a dream to working for ISRO as a computer engineer. So,
Yeah, as I mentioned to you that in case you'd like to see, there are two things I always tell when I give a talk. One is the talent and another is the passion. This ISRO is not the department which you must join it for the purpose of money, but it is your passion and your talent. Using that, in case you want to serve the country, this is the platform, because I'll tell you, after completing, I'm about to retire now, but my salary is very less compared to my colleagues which are working in the private industry. So if you are not money minded, if you are not want to become a millionaire or billionaire, I think you want to serve the country like our defense, then this is the place for you. You can do lots of research, and people are having free hand. Whatever they would like to do, they can do it. 24/7 labs are opened. High computing powers are available here. High power workstations are there. Many multiple core systems are available here for the quick calculations, and even for the rocket side, if you just see that we have multi-cores supercomputers are available in Vikram Sarabhai space centers for quick calculations, because duration will be small, and decision making is very important for a one mission to be successful. So lots of research is going on, and there is plenty of opportunity for all the engineers, including computer science.
One thing I would like to add, on 20th, we are going to inaugurate our offline session of this 2-week Atal FDP. In that, our keynote speaker is Shri Rajiv Chetwani sir. So he will talk a lot of things on the software related with satellite.
Yeah, I think just now Raji only was calling to me when it got disconnected. So Raji will be there with you. And Raji was here earlier in URO Satellite Center as a computer in charge, and later on shifted to headquarter. And he's looking towards our total cyber security, not only for our ground stations, ground support systems, but also for the space network and space assets. So you all get really benefited by his talk, his address. So if no other query from anybody, any audience, I think we can close down, Jen sir.
Yes, sir. Any question from the participants? Probably one possibility is there during 20th to 24th. If we get any slot, empty slot, then again I will prefer to request to Alok sir to present the slides. This is one
Yeah,
of the possibility.
I will try to do that. I'll try to see that. I think just let me see my calendar. 22nd to 24 may be possible. I think one of the day, if time permits, I think if that day network is slightly okay, I think I'll keep a backup also with some other service provider like Geo or somebody. So I'm sure that I'll be in a position to support. So I'll try to join that time.
Definitely, definitely. Thank you very much, sir.
Thank you.
So thanks a lot, Dr. Alok sir. You have
Thank
given
you.
your valuable time in spite of all obstacles and a remarkable contribution, commitment for our FDP. You are available here so late night even. So that is appreciable. And I hope next time we'll get your services also. Same way, sir. Thank you
Thank
very
you,
much.
sir. Thank you very much. And extremely sorry from the audience. I'm really sorry that due to the network issue, we couldn't show you the slide, which would have been very nice. But I'll share the slides with Jan sir, and I think all of you will be in a position to get some idea. And in case I get opportunity to talk to you once again, I'll try to do that. Thank you so much. God bless you. Thank you.
Thank you, sir.
Good
Thank
night.
you so much. All the participants, please fill up the attendance. Attendance link is working. We have put the attendance on group also, participant group also, but group is enabled. Group can be text by administrator only. So better you copy the link, take it on your computer, and fill from there. Thanks to all the participants.
हो गया सेशन
हाँ
हो गया सेशन
हाँ हो गया.